Welcome to Electrical and Electronic Principles for Neurodiagnostic Professionals. My name is Greg Niznik, and over the next several lessons, we'll explore the electrical principles behind the equipment we use every day in EEG, EMG, evoked potentials, nerve conduction studies, sleep, and intraoperative neurophysiological monitoring. Whether you're a student preparing for credentialing exams or an experienced clinician looking to strengthen your understanding of electricity and electronics, this course is designed to build your knowledge one concept at a time. You don't need an engineering background to understand electricity and electronics. My goal isn't to make you an electrical engineer. My goal is to help you become a better neurodiagnostic professional by understanding the electrical principles behind the equipment you use every day. Throughout this course, we'll build each new concept on the one before it. Rather than simply memorizing formulas, we'll focus on understanding how electricity behaves and how those principles apply in clinical practice. In this first lesson, we're going to learn the language of electrical units and measurements. Every day, we encounter measurements such as stimulation currents measured in milliamps, signal amplitudes measured in microvolts or millivolts, latencies and time bases measured in milliseconds, and electrode impedances measured in kilo-ohms. However, many of the formulas we'll use throughout this course are expressed using the base units of volts, amps, and ohms. To understand the magnitude of the measurements we use every day, and to use them correctly in electrical formulas, you first need to be comfortable converting between the metric prefixes used by our equipment and their corresponding base units. Once you're comfortable making these conversions, the electrical concepts that follow become much easier to understand. Fortunately, the metric system used in science and engineering is logical and consistent. Once you understand a few simple prefixes and learn how to convert between them, you'll find that the math is actually quite straightforward. By the end of this lesson, you'll be able to confidently convert between the common metric prefixes used in neurodiagnostics and understand the units you'll encounter throughout the rest of this course. Now, if the word math makes you a little nervous, don't worry. There won't be a math exam at the end of this lesson. Once you see how the metric prefixes work, I think you'll find they're much simpler than they first appear. Let's get started. Before we begin talking about metric prefixes, let's first spend a minute discussing the metric system itself. The metric system is the standard system of measurement used throughout science, engineering, and medicine around the world. It provides a common language that allows researchers, manufacturers, and healthcare professionals to communicate measurements accurately and consistently. Unlike the customary system of inches, feet, ounces, and pounds that we are familiar with in the United States, the metric system is based on powers of 10. That makes converting between units straightforward. In most cases, all you have to do is move a decimal point. For those of us in the United States, this can feel unfamiliar because we don't use the metric system extensively in our everyday lives. We think in miles rather than kilometers, pounds rather than kilograms, and inches rather than centimeters. However, in healthcare, and especially in neurodiagnostics, the metric system is everywhere. Every stimulation current, every EEG amplitude, every latency measurement, every electrode impedance, and nearly every specification in our equipment is expressed using metric units. Fortunately, once you understand how the system is organized, you'll discover that it's actually much simpler than the U.S. customary system most of us grew up using. Everything we'll cover in the remainder of this lesson builds on that simple idea. The metric system is built around a series of prefixes that tell us how much larger or smaller one unit is than another. Everything begins with a base unit. In this course, our base units will often be the volt, the amp, and the ohm. In other areas of science, the base unit might be the meter for length, the liter for volume, or the gram for mass. The purpose of metric prefixes is simple. They allow us to express very large or very small quantities using numbers that are easier to read, communicate, and understand. For example, consider a patient's weight. Suppose a patient weighs 95 kilograms. We could also write that as 95,000 grams. Both measurements are exactly the same. Both are equally accurate. So why don't we write patient weights in grams? Because 95 kilograms is much easier to read and communicate than 95,000 grams. The important part of the measurement, the number 95, is immediately recognized without having to count zeros. It also reduces the chance of making mistakes when reading, writing, or communicating the value. The same principle applies throughout neurodiagnostics. Instead of working with fractions of a volt or thousands of ohms, we use units such as millivolts, microvolts, and kiloohms because they make the numbers much easier to work with. Here is a chart with the standard prefixes for metric units. As you can see, here is the name of the prefix, the unit symbol, the number itself, and the base 10 exponent for the prefix. Fortunately, in neurodiagnostics, only a few of these prefixes are commonly used. Here's a chart showing the prefixes you'll encounter most often. Above the base unit, the most common prefixes are mega and kilo. Below the base unit, the most common prefixes are milli and micro. Now let's look at how to convert a value with a prefix to its base unit. If you look at the chart, you can see that the kilo prefix represents 1,000 times the base unit. So if we want to convert 10 kilo ohms to ohms, we simply multiply 10 by 1,000. In this case, 10 kilo ohms times 1,000 equals 10,000 ohms. An even simpler way to perform this conversion is to move the decimal point 3 places to the right. This gives us the same answer without having to perform the multiplication. An easy way to remember this is to compare the exponents of the two prefixes. Kilo has an exponent of 3, while the base unit has an exponent of 0. The difference is 3, so we move the decimal point 3 places. As a general rule, when converting from a larger unit to a smaller unit, move the decimal point to the right. When converting from a smaller unit to a larger unit, move the decimal point to the left. In this example, we're converting 10 kilo ohms to ohms, so we move the decimal point 3 places to the right, giving us 10,000 ohms. We can generalize the decimal point movement method with this 4-step process. Step 1, compare the exponents. Step 2, find the absolute difference in the exponents to find how many places the decimal must move. Step 3, determine whether you're converting to a larger or smaller unit. Step 4, move the decimal in the appropriate direction. Let's try another example, this time using our 4-step metric conversion method. Let's convert 80 millivolts to volts. Step 1, compare the exponents. Looking at the chart, we see that milli has an exponent of -3, while the base unit has an exponent of 0. Step 2, find the absolute difference between the exponents. The exponents differ by 3, so the decimal point must move 3 places. Step 3, determine whether you're converting to a larger or smaller unit. Millivolts are a smaller unit than volts, so we're converting from a smaller unit to a larger unit. Step 4, move the decimal point in the appropriate direction. Since we're converting from a smaller unit to a larger unit, we move the decimal point to the left. Starting with 80 millivolts, we move the decimal point 3 places to the left, giving us 0.080 volts. As you can see, using the 4-step metric conversion method, we have a quick and easy way of converting metric prefixes from one to another. Let's try one final example. Let's imagine you're monitoring a patient in the operating room. You're having difficulty obtaining a reliable response. The reading neurophysiologist asks you to increase the stimulus pulse width to 0.3 milliseconds. However, your machine displays pulse width in microseconds, so you'll need to convert the value before making the change. Let's use our 4-step metric conversion method. Step 1. Compare the exponents. Looking at the chart, we see that micro has an exponent of -6, while milli has an exponent of -3. Step 2. Find the absolute difference between the exponents. The exponents differ by 3, so the decimal point must move 3 places. Step 3. Determine whether you're converting to a larger or smaller unit. Milliseconds are a larger unit than microseconds, so we're converting from a larger unit to a smaller unit. Step 4. Move the decimal point in the appropriate direction. Since we're converting from a larger unit to a smaller unit, we move the decimal point to the right. Starting with 0.3 milliseconds, we move the decimal point 3 places to the right, giving us 300 microseconds. So 0.3 milliseconds equals 300 microseconds. On our stimulus parameter settings page, we select 300 microseconds. Our stimulus parameters are set correctly and we're good to go. In this lesson, you learned how to convert between metric prefixes using a simple 4-step conversion method. Once you understand the relationship between the prefixes and their exponents, these conversions become straightforward and easy to perform. In the next lesson, we'll build on this foundation as we introduce voltage, current, and resistance and learn the most fundamental relationship in electrical science, Ohm's law. If you found this lesson helpful, I'd appreciate it if you subscribed to the channel, gave the video a thumbs up, and shared it with your colleagues. My goal is to make high-quality educational content freely available to the neurodiagnostic community. If you have any questions or suggestions, please leave them in the comments below. I read every comment and will do my best to answer them. Before we finish, I'd like to mention one thing you may have noticed. The narration you're hearing is an AI-generated clone of my voice. I chose this approach for 2 reasons. First, it allows me to present each lesson with consistent pacing and clear pronunciation. Second, after a long day in the operating room, my natural voice becomes fatigued, and I wanted every lesson in this series to have the same quality from beginning to end. While the narration is AI-generated, the teaching, examples, and explanations all come from my own experience over more than 40 years working in neurodiagnostics. Thank you for watching, and I'll see you in the next lesson.